So could we get the YouTube broadcast? Yes. All righty. So then I don't think Monika needs another introduction. So I'm looking forward to the last lecture on gauge fields and some spin orbit coupling possibly.
Yes, unfortunately, I focused on gauge field. I hope that's okay. Yeah, so welcome to the last part of this lecture. And so yesterday, basically, I focused more or less exclusively on the Hofstadter model, which, to just briefly remind you, is a square lattice in the presence of a homogeneous magnetic flux. And we've discussed how to solve this problem, like how to define a proper magnetic unit cell and get the single particle energy spectrum. And the takeaway message would be that the new magnetic unit cell is larger than the original one because of the magnetic translation operators, and it contains an integer multiple of 2 pi of magnetic flux. And if you then calculate the single particle energy spectrum for various different values of the flux per unit cell, you get this beautiful Hofstadter butterfly, which has the self-similar fractal structure. And the measurement that I've shown you, the transport measurement in particular, was happening at a flux equal to 1/4, where we have these 4 subbands. And maybe just something as a side remark, because in the end, of course, we would like to go beyond single particle physics and include interactions at some point in order to study many-body physics in these topological band structures. I wanted to highlight that this value of 1/4 is actually not that bad, in a sense that the lowest band that we are working with, which is the one that is encircled in red, is relatively flat, and it has a relatively large gap to the next higher one. So if you compare to other ratios of the flux, like 1/3 or a different value, then actually this ratio is not that bad. So it has a gap to bandwidth ratio of 7, which means that it's relatively easy to include interactions, even if they're not so large, and study some interesting many-body physics. And actually the Landau level limit, the continuum limit, is recovered if you go to low values of the magnetic field. So actually down here in Hofstadter butterfly, where the value of the flux is very low, this is where you would recover the limit of Landau levels. All right, so for the second part, I would like to talk a bit more about the topology in hexagonal lattices and explain 2 more measurements on how we can extract the topological or geometric properties of these particular energy bands. And as a reminder, I'm not 100% sure if you have seen that in other lectures already, but the hexagonal lattice consists of 2 sublattices, A and B. So if you calculate the band structure, it's very similar to the calculation of the band structure of the SSH model. So we have this sublattices A and B, and we can interpret the cell periodic Bloch function in the end as this quasi-spinor, and think about how this quasi-spinor rotates in momentum space. So what you see here on the lower left is a schematic drawing of the real space lattice potential with these vectors D1, D2, D3. But then the primitive lattice vectors are the ones that are shown in orange. And then if we go to reciprocal space, the Brillouin zone is also a hexagon. And here you see the 2 reciprocal lattice vectors B1 and B2. And there are special points in the Brillouin zone of the hexagonal lattice, which are called K and K prime points. They are at the corners of the hexagon. And there are actually, as we will see later, there are other high symmetry points that have a name. So in the center at Q equal to 0, it's the gamma point. And then midway between the connection between K and K prime is the M point. Now, we can calculate the dispersion, the energy band structure for this hexagonal lattice. And so this is a cut through these 2 bands. So essentially you see the lowest band. So you see here this hexagon. And there are the Dirac points at the K and K prime points, which are at the corners of the hexagon. And the Dirac counts, if you expand the dispersion around these K and K prime points, it's linear as a function of quasi-momentum. But then what we are interested in is the geometric properties of the band. So we look at the barrier connection or the barrier curvature. And at these Dirac points, we have highly concentrated barrier curvature, like a delta function times pi, which changes sign depending on K and K prime. Yes, so the Dirac point, if you look at the dispersion relation, the name comes from the analogy to the Dirac equation.
Are you answering the question? Sorry.
Yeah,
okay.
I just started answering the question. But for now, if you look at the dispersion relation, you can just think of it as really, if you take an intersection, if you take a cut through the dispersion relation and you look at the band touching point, which is here, then you see that it's linear around this point. Okay, so at these points, we have this highly concentrated barrier curvature, which are delta peaks. And we can calculate the barrier phase or the geometric phase around one of these Dirac points. And this will give us this very characteristic value of the barrier flux that is equal to pi. And this actually changes sign between the K and K prime points. So if we were to evaluate the same integral around the K prime point, we get minus pi. And one of the first things that you may want to do is actually measure this pi barrier flux of this very famous dispersion relation. And in cold atom experiments, we can generate the hexagonal lattice relatively easily by interfering 3 laser beams. So they interfere under 120 degrees. They create this hexagonal shaped optical lattice. And here the beams are blue detuned with respect to an internal transition. And they are linearly polarized, as shown by this dot out of plane here. And something else that turns out to be a very useful tool for studying the band structure and the geometric properties of the band structure is that we can apply a force, as I mentioned yesterday, but I didn't really tell you how we apply the force. So you can actually either do that by tilting the lattice, but you can also do that by accelerating the lattice. And in particular, if you choose the 3 frequencies of the 3 laser beams to be equal, you get a static interference pattern. But if you detune the frequency of one of the 3 beams, you accelerate the lattice potential in one direction. And in principle, by changing the detuning as a function of time, you can engineer any arbitrary accelerations. And in particular, if we choose to change the detuning linearly in time, we can create a constant acceleration. And then the idea is that in the reference frame, co-moving with the lattice, this looks like a constant force. So on the left, you see actually 2 schematic drawings for the lab frame and the lattice frame in reciprocal space. So since we are accelerating the lattice, we have and let's say we prepare a wave packet in the lowest band, let's say a condensate at Q equal to 0, we are actually moving or dragging the lattice across the cloud. And so the BEC will actually remain at Q equal to 0, but effectively what we are doing is we are moving the brewing zone. And now if you sit in the reference frame co-moving with the lattice, what happens is that now the Brillouin zone in quasi-momentum space is fixed, but you're changing linearly the quasi-momentum as a function of time, which is what you would also get if you just apply a tilt to your lattice potential. So if we start at the gamma point, which is the Q equal to 0 point, we change the quasi-momentum linear as a function of time proportional to the force F, and scan, if we do that adiabatically, we can scan the wave packet or the quasi-momentum of the wave packet through the full Brillouin zone. This is also what is shown in the schematic on the right. So if the force is small enough, then this change of quasi-momentum will happen adiabatically, and we just move it through the lowest band. And this is very useful because it allows us to realize a spectroscopy technique in order to measure the band structure or to probe the band structure of this two-band lattice model. So the two bands of the hexagonal lattice. Okay, so let me explain how this works. That's typically known as Stuckelberg oscillations. So we start with a condensate or wave packet, which is illustrated as this red dot in the ground state of the band, so at q equal to 0. Now we apply this acceleration, or we apply the force in order to change the quasi-momentum of the wave packet linearly as a function of time. Now, if the force is small, we would probe the band adiabatically, so the atoms would remain in the lowest band. But now there are special points in the Brillouin zone where the bands become closer to each other. And if we now choose the force large enough, we can have Landau-Sehner transfer to the excited band. So there can be a non-adiabatic transfer. And in an interferometry language, this would be something like a beam splitter. So we have our initial wave packet, and then we split it along two different paths. So they explore the lowest and the first excited energy band. And then we can move the wave packet up to a final position in this dispersion relation, which is here denoted as capital Q, and introduce a hold time. So we just wait there as a function of time. And then we reverse the acceleration or the direction of the force and move the wave packet back to its original state. And the force, the strength of the force is the same. So after having had this hold time at the final quasi-momentum capital Q, we go across this avoided band crossing. We mix the two fractions again. And after, so this would be the second beam splitter of our interferometry sequence. And at the end of the sequence, we are back at Q equal to 0. And there we can now measure the fraction of atoms in the lowest band, for example, as a function of this whole time that we have introduced at the final quasi-momentum capital Q. And what happens at this point is that because we have this coherent superposition between a fraction of atoms in the lowest band and in the first excited band, they will oscillate as a function of time according to this difference frequency, difference in energy between the two bands. So by mapping or by extracting the fraction of atoms in the lowest band after this interferometry sequence as a function of time, we can extract the oscillation frequency, and from that we can extract the energy gap between the two bands. And this is one example as it would look like in an experiment, where you see indeed N1 means the fraction of atoms in the lowest band as a function of time. So you see this nice oscillation. And the fraction in the lowest band is extracted after a band mapping technique. So when we turn off the lattice adiabatically, then quasi-momentum is mapped to real space momentum. And just by counting how many atoms end up in the center here, you can extract the fraction of atoms in the lowest band. So here you see that there are additional peaks outside of the one at Q equal to 0. And these are atoms that were transferred to the higher band. Okay, so from this oscillation frequency, we can extract the energy gap at this specific point in the Brillouin zone. And now by scanning different final positions, we can in principle map out the whole band structure. And here's two examples of a measurement that was taken in the lab, where originally we start here with a condensate at the gamma point at Q equal to 0. And then we transfer it or move it through different points in the Brillouin zone. So here's the M point, which is midway in the connection between K and K prime. There's the gamma point, and here below there's the K point. So here you see a scan of the energy gap as a function of the quasi-momentum, where we introduce the hold time. And in particular, you see here that the gap starts to become smaller and smaller as you approach the Dirac cone at the K point, where we know that there's a band touching point in the band structure. And then, of course, here the measurement doesn't work anymore. The frequency will become smaller and smaller. And using this data, one can actually very nicely calibrate the lattice depth. So by just fitting the shape of this energy gap, you can extract here that the lattice potential is 0.8 E recoil deep or 2.5 E recoil deep. Okay, so now this has been the scalar part. Sorry, there was a question.
Yeah, sorry, it's the sequence of 5 pictures that you had. It looked like the atoms in the excited band were also at Q equals 0. So how did they end up moving to a different place in real space?
Yeah, I didn't really explain that. Yeah, so that's a very good question. So we have the cloud prepared in the lattice. And normally if we suddenly switch off the lattice, so that's how we measure the atoms after time of flight. So typically we suddenly switch off the lattice and then you see many diffraction peaks. But if you turn off the lattice adiabatically, then the quasi-momentum distribution is mapped onto real space. So actually the atoms that are in the lowest Brillouin zone, the quasi-momentum will be mapped onto real space, which then also shows, has the shape of the Brillouin zone. But if the atoms are in a higher band, then this quasi-momentum will be mapped to the first excited Brillouin zone, and they appear at different locations in the real space momentum distribution.
I see. Okay, thank you.
And then we can draw little boxes and simply count the fraction of atoms that ends up in the lowest band.
Gotcha. Thank
you.
So
this is what you see here. So the center, so if you draw here a hexagon, that would be the first Brillouin zone. And here we have only Q equals 0 populated in the lowest band. So if you draw a box around the center peak, that would be the fraction in the lowest band. And then the ones out here, they are atoms that are in the excited band.
Okay, cool. Thank you.
Okay, so this has been actually the scalar part, so the dispersion relation of the hexagonal lattice. And now the idea is to find another protocol that allows us to also extract the geometric properties. And the way this works is very similar to the Aharonov-Bohm interferometer that is performed with charged particles in real space. So quick reminder about what the Aharonov-Bohm effect is about. So if we have an electron wave packet, we can generate an interferometry sequence. So we split the electron wave packet along 2 different paths. And then the phase that is measured at the end of this interferometry sequence, the Aharonov-Bohm phase, will depend on the vector potential or the magnetic flux that is piercing the area of this interferometer. And we can express that in the language of geometric phases. So A is the vector potential, but you can think of it as the Berry connection here in real space. And if we evaluate this phase around a closed loop, here labeled as C, then we can use Stokes' theorem in order to express it as an integral over the magnetic field, over the area of the interferometer, which gives us the magnetic flux. So this is our Aharonov-Bohm phase. And now we try to do something similar, but in quasi-momentum space, which is where the topology or the geometric properties of the band are defined. So what we have in mind is actually taking a wave packet, as we have discussed, a BEC, prepared at a certain position in quasi-momentum space. We know how to move the wave packet around by applying forces. And so the only thing that is missing is that we can split the wave packet along 2 different paths. And then if we evaluate the geometric phase or the Berry phase at the end of this interferometry sequence, it will be also given by the integral of the Berry connection around this loop of our interferometer. Or equivalently, it will be the integral over the Berry curvature over the area of this interferometer. So in principle, if you build tiny little interferometers, you could map out the local Berry curvature distribution across the whole dispersion relation. And this has been implemented in order to measure this pi Berry flux that is associated with the Dirac cone in the dispersion relation of the hexagonal lattice. Okay, so let me explain how the interferometry sequence was implemented in the experiment. So initially, we have a condensate at Q equal to 0. So there's some wave packet. And usually we only work with one internal state of the atom. So let's say the lowest energy state in the ground state hyperfine manifold. But now we can use additional fields, microwave or F fields, in order to create a coherent superposition between two different Zeeman states. So this is indicated by this pi/2 pulse here. We work in this case with rubidium atoms in a Zeeman level 1-1. But now if you make a pi/2 pulse, you can couple to the F equal to 2 manifold. Let's say F equal to 2, MF-1. And those two states have opposite magnetic moments. So at this point, now we have a coherent superposition between spin up and spin down. And now we manipulate the wave packet. So we already know one way to manipulate it, that is by applying the acceleration. But this will move both states in the same way. However, if additionally we use a tilt, which is realized with a magnetic field gradient, the two spin states or quasi-spin states will respond opposite to the applied tilt, because they have opposite magnetic moments. So if we combine the two, we have an acceleration here along the y direction and a magnetic field gradient perpendicular to it. The wave packet will split into two parts, because spin up atoms will be dragged to the right and spin down atoms will be dragged to the left. So this opens again our interferometry sequence. And now this shows the hexagon in quasi-momentum space. So that's the first Brillouin zone of the lattice. So here at the corners, again, we have the K and K prime point. So if we want to measure the flux, Berry flux associated with the Dirac cone at the K prime point, we want to enclose this in our interferometry sequence. Okay, so now we have to bring them together again because we want to make them interfere in order to read out the relative phase at the end of the interferometry sequence. And this is done by applying a pi pulse in order to switch the populations between spin up and spin down, as shown here. And then if you keep applying the same forces as before, still there will be acceleration along the y direction, which moves the wave packet along y. But now spin up will be dragged to the right again, so they will actually move towards each other. And if you do that midway through the interferometry sequence, at the end, they will overlap again. They will be in the same quasi-momentum mode. So at this point, we close our interferometry sequence. And then in order to measure or extract the relative phase between spin up and spin down, we can apply a Ramsey sequence. So we read out the relative phase by rotating the state on a Bloch sphere and scanning the phase of the final pi/2 pulse that we apply. And then in the end, we measure the fraction that ends up in spin down and the fraction that ends up in spin up. And this is the experimental result. So I covered half of it. So again, here on the upper left corner, you see the Berry curvature distribution, which is strongly peaked at the K and K prime point. And here in this little schematic, you see different interferometry areas. So we always start at the gamma point. But then the final point of the interferometer is scanned across the Dirac point, across the K point. Okay, so here gamma, if you look at this dashed line in the center, this would mean there's no interferometry sequence or the area of the interferometer is 0. And then the final point is scanned. So the Berry phase or this geometric phase that is extracted remains equal to 0 because there's no Berry curvature in the center of this Brillouin zone. It's only peaked at the K and K prime points. And then as soon as you start enclosing one of the Dirac points, the phase jumps from 0 to pi. And then it remains at pi until the area of the interferometer becomes so large that the K prime point, the second Dirac point, is enclosed in the interferometry sequence as well. And at this point, those two contributions cancel. And again, we measure a phase of 0. And these insets that you see here, they are actually the Ramsey sequences in order to extract the geometric phase. So there are two curves. So you see always the population spin down is measured. There are two curves. The black one is actually a reference sequence, because there can be always systematic phase shifts that appear in your experiment, which may not be cancelled. So the black one is actually a reference sequence where the interferometer is opened and then closed again, but without the pi pulse. So this, strictly speaking, does not enclose any area if you apply the sequence. And then for the same length of the interferometry sequence, now if you apply the spin echo pulse, so you actually open up the whole area of the interferometer, you get the blue data points, and the relative phase between the two gives you the geometric phase. And the second half of this plot actually shows the interferometer that was performed in the opposite direction, so by reversing the lattice acceleration or the force along y. Okay, so I was assuming that you actually heard, at least in one of the lectures, what this geometric phase or the Berry phase is about. So maybe at this point, let me ask you if there was maybe something in this explanation that I swept under the rug when only talking about the Berry phase or this geometric phase that we would like to measure. I guess there's something that I forgot to mention, or that we should be careful about. If you haven't heard about this before, actually, maybe also let me know. Maybe if it was not covered in Nigel's lecture, for instance, then maybe I explain it in more detail.
Yeah, we did have some lectures that used the geometric phase and Berry phase, Berry curvature.
Right. Okay, that's good. So is there something that I missed that I should have commented on, maybe?
Is there an intuitive explanation for why the Berry phase is so peaked around the K and K prime points?
Well, there is an explanation. I'm not sure it's very intuitive, but the band touching point at the Dirac point is like a monopole, or it's the source of Berry curvature. If you look how the spinor, this quasi-spinor, winds around this Bloch sphere in quasi-momentum space, this is associated with the field of a monopole. And so if you integrate over it, you get a pi Berry flux. But I'm not sure that's very, very useful. Or, well, intuitive.
Thank you.
Was this covered, the monopole?
Yes.
Okay. So actually what I wanted to get at is that apart from these geometric phases, there are other contributions, which is known as dynamical phase, which one has to worry about. So let me just briefly mention again what this is about. So the concept of measuring this geometric phase relies on measuring the Berry phase. So what we think about is doing some adiabatic evolution in an abstract parameter space R. And we do it around a closed loop. So here we can think about this R as being higher dimensional vector. It could be had contributions R1, R2 up to d dimensions. In our case, it would be just Qx and Qy. And we can ask about what the phase or what phase the wave packet picks up at the end of the sequence. And for that, we define the instantaneous eigenbasis. So we have a Hamiltonian that lives in this abstract parameter space R, and our eigenstates we just denote as n of R, and they will have some eigenenergies E of R. And now if we solve the time-dependent Schrödinger equation, we can calculate the state psi of t after we performed this adiabatic evolution in our parameter space, which in our case is Qx and Qy. And then you will find that there are two contributions to the phase that the state picks up. So at the end of the closed loop, you retain to your original state that you have started out with. But then it picks up this phase. And the first one, gamma n, is the one we are interested in. That's the geometric phase. But there's a second contribution, the so-called dynamical phase, which depends on the energy of the band. And so this geometric phase is the integral over the barrier connection, which in this case is defined as the derivative with respect to r, in our case, the derivative with respect to qx, qy. Okay, so there's this additional term, the dynamical phase, that one has to be careful about. And so if we go back to this interferometry sequence that I've shown you, it has actually been chosen in a very clever way, because we start at q equal to 0, and then it's open symmetrically. And if the dispersion relation is perfect, as we would expect for a hexagonal lattice, the energy that is explored along these two paths is exactly the same, such that in the end, if we read out the relative phase, this contribution of the dynamical phase cancels. Okay, so we don't have to worry about in this interferometry sequence. But if you choose different areas of the interferometer, that's indeed something that you may have to worry about if the dispersion that is explored during this interferometry sequence is not exactly the same. Okay. So now this is actually the trivial or, well, the usual hexagonal lattice. But now in order to make it topological, we need to do something else. And in particular, we want to open a gap at the Dirac points, because only then we can calculate a well-defined Chern number for the two separate bands. And if we make this model topological, or one way to do that is to realize the Haldane model. And the Haldane model is special because it's not characterized by a net magnetic field through the Brillouin zone, but instead it has a staggered field. So if you calculate the phase around the borders of this hexagon, it's equal to 0. Now, in addition, there's no breaking of the translational symmetry. So all these issues or all these subtleties that we discussed for the Hofstadter model, they do not really play a role. So I have two bands, and in the Haldane model, I again have two bands. They are now gapped, but I don't have to worry about any splitting of the band into magnetic subbands, which makes it actually very nice for studies in synthetic quantum systems. So the Haldane model is a tight binding, in the tight binding form, has here real nearest neighbor tunnel couplings, which are denoted as Tij, and complex next nearest neighbor hoppings with the phases phi ij. And there can be a sublattice energy offset delta between the two sublattices A and B. Now, the hexagonal lattice in its original form is time reversal symmetric and inversion symmetric. And actually the Dirac points where the two bands touch, they are protected by these two symmetries. So if we open up a gap, we need to break either inversion or time reversal symmetry. And one way to do that, to break time reversal symmetry, is by applying circular shaking. And this, I think, has been covered by Tillman, so I will not go through the Fouquet calculation of that. I just want to mention the two realizations. The first one, which was realized in Tillman-Esslinger's group, but the very first experimental realization was actually done in coupled photonic waveguide arrays. So you see this photonic waveguides, which are shown in gray, and they have these wiggly lines. So time in this case is actually the propagation in plane. So this has this circular shaking of the individual lattice sites, which breaks time reversal symmetry and which allows you to implement the Haldane model in this Fouquet framework. Okay, so originally our band structure looks like this. So these are pictures I've taken from the ETH group. We have two bands and they touch at the Dirac points. Okay, so these two are protected by inversion and time reversal. So time reversal symmetry, you can just think about applying complex conjugation. So if we apply complex nearest neighbor hopping matrix elements in this model, we break time reversal symmetry, and this opens a gap between the two bands. Similarly, we can break inversion symmetry by applying a sublattice energy offset between A and B sides, which would also open a gap. And this leads to the phase diagram for the Haldane model, where you see the different topological phases. So along the horizontal axis, you see the phase of the complex next nearest neighbor hopping, which here is now a different phi, but that's the complex next nearest neighbor hopping. And delta AB is the sublattice energy offset between A and B sides. So if you don't break time reversal symmetry, we stay here at phi equal to 0. So if we look at along this vertical line here through the phase diagram, at the center, we have the usual dispersion relation of the hexagonal lattice. There's a band touching point at the K and K prime points, the Dirac points. And then if we add a sublattice energy offset, we open a gap, but the Chern number of the two bands remains trivial. So we have Chern number equal to 0 for the lowest and to the first excited band. Now, we could also look at what happens along the horizontal line. So starting from the central point, we can break time reversal symmetry by the circular shaking and explore this regime along the horizontal line here. So again, in this red regime and the blue regime, there's a gap at the Dirac point that opens up. But the sign of the Berry curvature at one of the 2 points flips, such that if you integrate the Berry curvature over the full Brillouin zone, you will find that now you have bands with non-zero Chern number. So for the lowest band here in the right region, in the red region, you have a Chern number equal to -1. And in the blue region, a Chern number equal to +1. And the first excited band then has the opposite sign. Okay, so using the circular shaking and the sublattice energy offset between A and B sides, we can explore the different regions of this Haldane phase diagram. And there's actually a very nice way to probe directly the Berry curvature distribution quasi-momentum resolved, which is a technique that has been implemented by the Hamburg team. And I would like to briefly sketch the idea. So in the upper right, you see how the hexagonal lattice is generated. So again, it's generated by interfering 3 laser beams. And if you play with the polarization of these 3 beams, you can imbalance the lattice such that either the A or B sublattice wells become deeper. So this allows you to introduce an energy offset between the 2 sides. And the circular shaking can be implemented by introducing this frequency detunings between the beams, which we also used in order to accelerate the lattice. Okay, so we have all the ingredients to tune the different parameters of the Haldane model. And now the question is how to extract the Berry curvature. And these measurements, they were actually done with fermionic atoms, where the Fermi C occupies the complete lowest band, all quasi-momentum states. And the key ingredient that is used in the sequence is a projection to a hexagonal lattice with very large AB sublattice offset. And in this case, you basically decouple all the sides. So the bands become flat, and the energy difference between the bands is given by the sublattice energy difference delta AB. And this is what you see here for one specific value, where delta AB is a little bit larger than 11 kilohertz. So you see that if you apply this very large energy offsets, you have these 2 separate bands, which are very flat, and the energy difference is basically constant as a function of quasi-momentum. Okay, so then the idea is to study the geometric properties by projecting onto these bands. Okay, so let's see how that works. So initially, there will be a very large energy offset, and the atoms are adiabatically prepared in the hexagonal lattice. So they will actually preferentially accumulate on the B lattice sides, and there will be nothing on the A sublattice sides. This is illustrated here. So you see the 2 flat bands. There's a red dot down here indicating that the atoms populate the lowest band. And now you can think of the band structure or the eigenstates and how they vary as a function of quasi-momentum by thinking about quasi-spinors. So we have these two component vectors, very similar to the SSH model. So we can define a Bloch sphere for this quasi-spinor. So we have the poles, which are shown here, which are defined as occupation on B or A sublattice sites. And you can think about this Bloch sphere for each individual quasi-momentum. And now for the initial state, this will be represented as a vector that is pointing up on the Bloch sphere because only B sites are populated. So then the atoms are adiabatically transferred into the Floquet bands. So the circular shaking is turned on adiabatically, which gives you the dressed bands, as illustrated here. And those will mix A and B sites. So in this case, they actually choose a near resonant shaking. So the modulation is at a frequency that is slightly detuned from this delta AB sublattice energy offset. Okay, so the bands become mixed, and the color is represented here on the Bloch sphere. So the state, if you think about the quasi-spinor, can be expressed in this form. So there will be a mixing angle theta, which mixes Ka and Kb, and some angle phi on the Bloch sphere. And these angles are essentially what we want to determine, because those angles and how they change as a function of quasi-momentum allow us to calculate the Berry curvature. Because if we know these angles theta and phi as a function of quasi-momentum, we essentially have all the information about the eigenstates. And if we have all the information about the eigenstates as a function of quasi-momentum, we can compute the Berry curvature from that. Okay, so now the atoms are adiabatically prepared in distressed bands. And now suddenly those are projected back onto the flat bands. And now what happens is that these quasi-spinors, they precess around the poles of the Bloch sphere. And they precess around the poles with a frequency that is given by the gap, by the energy difference between the two bands. And now after a time of flight experiment, the density distribution that they get oscillates as a function of time. So what you see here is a momentum resolved measurement. There are 3 different points, 1, 2, and 3. And for each quasi-momentum, they observe these oscillations as a function of time. So what they do is they really evaluate each individual pixel. This gives them their quasi-momentum resolution. And then from these oscillations, they can extract the phase of the oscillation and the amplitude of the oscillation, which is the amplitude and phase that appears in the eigenstates. And from these values, so this is what you see in this summary plot. So on the left, you see the amplitude of the oscillation that they extract for 2 different chiralities of this modulation that they apply. You see the phase. And now from these 2 quantities, they compute the momentum resolved Berry curvature. So here the blue area is negative Berry curvature, and the red area are regions of positive Berry curvature. And then by summing up all these Berry curvature values within the first Brillouin zone, they can extract the Chern number of the band, which in this case is equal to 0, but the technique also works for non-zero Chern numbers if the modulation parameters are chosen differently. So I think this is a very nice technique that also highlights how these synthetic quantum systems can be used in order to study these maybe rather abstract concepts of geometric phases and geometric quantities by directly mapping out what these distributions are and how they are modified as a function of the lattice parameters and the modulation parameters. Okay. Are there any questions, maybe? Okay, so if not, I would like to spend the last or the remaining time to show you a few ideas of how to go beyond what we have been discussing so far. So in principle, all these Fouquet engineering techniques, they were meant to emulate something that we can otherwise not study in our cold atom systems. So I told you that having this quantum Hall system in mind, we would like to engineer some artificial magnetic field in order to recreate this in experiments. So as a reminder, in the integer quantum Hall effect, we have these plateau values that are very precise and only depend on integers or the Chern numbers that characterize the topology of the bands which are occupied by electrons. And in particular, there's a direct correspondence between the Chern number of the band and the number of edge modes at the edge of a finite system. However, now that we have implemented this Fouquet engineering technique, you may also use it in order to realize something that otherwise you will not be able to get. So the idea is to go away from what we have called the high frequency limit. In the high frequency limit, we were able to use the series expansion in powers of 1 over omega in order to calculate the effective Fouquet Hamiltonian. Now, if we go away from this limit, the situation becomes much more complex, because now we don't have this nice separation of energy scales, which allows us to take omega to infinity. In this case, it can be on the order of the tunnel coupling, for example. So we have to be more careful about analyzing the properties of the system. And just to remind you again how this high frequency limit works, we have calculated this effective Fouquet Hamiltonian, which has a certain band structure, but then we completely forget about the other copies, that we have this extended series of bands. And then we apply the usual techniques to calculate the Berry curvature, geometric phases, and Chern numbers, and so on. So we completely forget about that we have actually generated a time-dependent system. So now it's interesting to ask what happens if you cannot do that. So if you actually have to take into account the time dependence explicitly. And this can be used to generate a new situation where you can have edge modes, although the Chern number of the band is 0. Okay, so there's a modified Bike edge correspondence, which does not allow you anymore to use the usual tools that you know, just computing the geometric properties of the Fouquet Hamiltonian, to predict if there are edge modes in a finite system or not. And the reason why this can happen in a periodically driven system is that we have this extended zone scheme, or the quasi-energy spectrum, where the quasi-energy is only defined up to an integer multiple of h bar omega. So this point down here in the Fouquet-Brillouin zone is equivalent to the one up here, which means that there can be an edge mode entering the spectrum, or the Fouquet zone spectrum, from below. And the reason why this can happen is because there's no true notion of a lowest energy band. But usually in a static system, this cannot be the case, because this edge mode cannot just end somewhere. But here it can wrap around the quasi-energy Brillouin zone. And there's a direct connection between the number of edge modes above and below a Chern band. The difference between the two is equal to the Chern number of the band in between. So in this example in the lower right corner, we actually do have edge modes in the system, but if you calculate the corresponding Chern numbers of these two bands, they are equal to 0. And this is interesting because, first of all, it's a new topological regime that you cannot really have in a static system. And it's predicted that this phase is even more robust in the presence of disorder as a conventional quantum Hall system. And the intuitive argument why that may be the case is that you have this edge mode that runs around the full Brillouin zone. So even if you actually localize the whole, all the states in the Bike bands by applying disorder, it will not immediately kill the presence of the edge state. So for a conventional quantum Hall system, you may expect that if you apply disorder, that as soon as it becomes too strong and starts mixing the two bands, which have opposite Chern numbers, then there will be a topological phase transition to a trivial regime. However, here it's expected that this will not happen, or at least will happen at this order value that is much larger as compared to the critical one for conventional quantum Hall system. Okay, so how can we actually realize something like that in experiments? Or maybe let's first let me first walk you through one of the first examples that have been suggested for realizing such a new topological phase, which is called anomalous Fouquet. And there's a very simple protocol that can be implemented in a bipartite square lattice, where again we have A and B sublattices, and they are shown as black and white dots. And the idea is to implement a 4-step protocol where tunneling is only turned on along the colored bonds. And we can choose a very fine-tuned situation where we choose this 4 steps of the modulation protocol, such that a wave packet that was initially prepared on one of the sublattices, let's say on the black side, for this first time step where tunneling is turned on along the red bond, has exactly the amount of time it needs to tunnel from the black to the white lattice side. So if we prepare this initial state, let's say a wave packet or localized particle on the black side, and we follow this 4-step modulation protocol, during the first step, it will tunnel to the white side here. Then during the second step, it will tunnel along the blue bond down. Then it will tunnel to the left along the green bond, and it will tunnel up along the white bond. And after those 4 steps, it will actually return to its original position. So if you write down the Fouquet time evolution operator for that specific driving protocol, so we look at one oscillation period, capital T, it will be the identity and nothing happens, which means that the Fouquet Hamiltonian is trivial. It vanishes. And if you calculate the spectrum, you get 2 degenerate flat bands with trivial topology. However, there is something happening at the edge. So if there's a wave packet or localized particle prepared at the edge, it can go only along one direction. So if we start with a wave packet or particle prepared on the white side, during the first step, it can tunnel over here along the red bond. During the next step, because we turn on the blue tunneling like this, it cannot tunnel. And then during the third one, it can tunnel again one side further. And then during the yellow one, it cannot tunnel again, because here there's no bond that has been turned on. So here you see that it's essential to have this AB bipartite square lattice. And on the lower edge, the same. So there's still some chirality associated with this driving protocol. And as you can see, it's related to what happens within one driving period. Because if I would not tell you what are the intermediate steps, you were not able to predict what happens at the edge. And this gives you a hint of how to describe these anomalous Fouquet systems. It means that now, because we cannot apply this high frequency limit, the micromotion or what happens within one driving period does start to play a role. And then we start to have these edge modes appearing in the quasi-energy spectrum. Okay, so this is in summary what I've just said in words. So it's not enough to look at the topological properties of the Fouquet Hamiltonian. We need new tools in order to understand the full topological properties. And we see that the micromotion or the full time dependence becomes important in order to get or understand this non-trivial winding of the quasi-energy spectrum. So this implementation protocol or variant of this modulation protocol has been first realized again in coupled photonic waveguide arrays. And in these experiments, time, as I mentioned before, goes in the propagation direction Z. And the coupling between neighboring sites is determined by the distance between neighboring waveguides. So in order to have this modulation protocol where tunneling is turned on along one bond and then along the other, can be realized by bringing the waveguides closer together. And so what they can do is actually launch light or photons into one specific waveguide and then see how they propagate. And so if they want to scan the time for this time evolution, they have different lengths of these waveguides, and they show, or they look at where the light exits on the end facet of this waveguide array. And what you see is that indeed for this modulation protocol, there's an edge mode. There's a propagation where the light only moves around the edge. It does not leak into the bulk. And this happens even if you add defects, which shows the topological nature of these edge modes. So there's no backscattering. The particles will follow the edge. And in the bulk, you see that there's no transport. So the states in the bulk are actually localized. So in this 4-step modulation protocol, if you were to look after integer multiples of the modulation period, the light will remain always localized in this waveguide here. Okay, so in our case, we use a slightly different lattice. We don't use the bipartite square lattice, which is a little bit more complicated to realize, but we use the hexagonal lattice, which is periodically modulated. Now, in order to see that we have actually generated some new topological phase, we should also think about characterizing the topological properties. So we have ways to extract the Chern number, for instance, using transport measurements or using this quench protocol state tomography technique by the Hamburg team. But if we cannot directly look at the edge modes, we have to find another way to characterize the topological properties. Now, just from a theoretical perspective, we also need an additional topological invariant that allows us to characterize the system. Because, previously it was enough to have this bulk edge correspondence between Chern numbers and edge modes. So if we know the Chern numbers of the bands, we know what happens at the edge. But here, this is not the case anymore. So we need a new topological invariant that fully characterizes the system. And there are winding numbers that can be computed from the time evolution operators. And these winding numbers, they directly determine the number of edge modes that live within a certain gap. So here W0 would give you the number of edge modes around 0 energy, and W pi would give you the number of edge modes at the edges of the Floquet brilliant zone. And then the difference between the winding numbers above and below a band is equal to the Chern number. But now these two winding numbers are two independent quantities which fully characterize the system. If I know these two Chern numbers, C minus and C plus, they are not enough because those are not two independent quantities. The sum of C minus and C plus has to be equal to 0.
There's a question.
Right, so the question is, what is winding in these winding numbers? Yeah, so that's a good question. So it is, if you want the propagator or the time evolution operator, which you write down as a function of time, but now not capital T, but small t. So you track what happens during one driving period, and evaluating this integral or the winding of this propagator gives you the winding number W in the end. So I have actually not put the formula, which I probably should, but you can look it up in this reference here by Rudner, for example, where this is nicely explained. So we can compute the winding number from the time evolution operator U of t, but taking into account how it varies within one driving period. And so this W then gives you the number of edge modes within a certain gap. And if you're able to extract this winding number, you know all the topological properties of the system. Okay, the question is how we can get to those, or how we can get information about those without having to look at edge modes directly, which is something that's not very easy to do in our type of experiments. And the way this can be done is making use of the bulk geometric properties again, because this is what we know how to measure. We can measure geometric phases or Berry curvatures, for instance, and if we can track those and how they change, we know how the topological properties change. So the idea is to start in a well-known limit, which is typically the high frequency limit, where we can apply the rotating wave approximation, we can map it to a static system, and there we have our usual Bike edge correspondence that we understand very well. And so in this particular case, which I'm getting to how we actually implement it, but it's also a hexagonal lattice with some type of chiral modulation. And we know that if we have a very high frequency modulation, this allows us to open a gap at the Dirac cones to break time reversal symmetry and make the Chern numbers of the two bands non-zero. So this is what I denote as the well-known high frequency limit, where the Chern number of the two bands is equal to plus and minus 1. And we have an edge mode around zero energy. So here, if I forget about all the other copies in my Floquet spectrum, I'm fine, because this I can map to a static Hamiltonian, which is described by the Haldane tight binding model. And now starting from this limit, I can try to understand what happens at the topological phase transitions as I vary my modulation parameters. So what I want to do is understand what happens at the gap closing point. So we know that the topological properties can only change if we close the spectrum between the two bands. And now the only thing that I need to do is understand what these spectral gap closing points do to my system and how they change the geometric properties of the band. Okay, so here's how the protocol works. We start in this high frequency limit, but then, as I will show you in a second, you can think about varying one of your parameters in the Hamiltonian in order to cross a topological phase transition. So you change one of the parameters of the system, which induces a gap closing point, and then the topology of the bands may change after this gap closing point. And we characterize this parameter that allows you to drive across a topological phase transition as lambda. So now we have generated this artificial parameter space, 3D parameter space, which is governed by Qx, Qy, our quasi-momenta, and this additional parameter lambda. And here's one example. So here you see what can happen as a function of lambda. You see two copies of the Floquet zone separated by h bar omega, and there's a gap closing point between Floquet zones. Okay, so now this gap closing point itself in this 3D parameter space Qx, Qy, lambda has a topological charge or has topological properties, which we can try to measure in experiments. And in this 3D parameter space, it's equivalent to a y point. So we can assign a topological charge to it, which for linear gap closing points, it's either plus or minus 1. And the sign of this topological charge, which is the source of how the geometry of the bands change, determines how the winding numbers change. So in this case, if there's a gap closing point between Floquet zones and this topological charge were to be plus 1, it changes the winding number in this gap by plus 1. So if there was no edge mode before, after this gap closing point, we would have one edge mode between Floquet zones. And since for this type of gap closing points, only the sign of the topological charge is relevant, it's enough to extract the sign of this topological charge from experiments. And in order to know which one of these winding numbers changes, so sorry, I should explain the gap, these epsilon here as well. So we have this topological charge, which is denoted as Qs, S for singularity. And this epsilon, it just means we look at the winding number just before the topological phase transition and just after the topological phase transition. And lambda S is the point where the topological phase transition happens or where there appears a singularity in the spectrum. Okay, now in order to know which one of the winding numbers changes, we also need to know which gap closes in the spectrum, because you know there could be either a gap closing point here or there could be one around in the middle of the spectrum. And then either this winding number would change or the other one. Yes, I will come to that. I actually No, actually, you see it right here. Now, let me explain the question directly. So the question is about the gap closing point between Fouquet zones. And what you see here, so if we are in the very fast driving limit, then these two copies would be very far apart. And the bandwidth of these two bands is actually given by the tunnel coupling, roughly by the tunnel coupling between neighboring sites that determines the width of the two bands. So this is the energy scale J. So now if you decrease the modulation frequency, the copies of the two spectra will effectively move closer together. And let's just for simplicity assume that this modulation frequency does not affect the bandwidth. We just assume that the bandwidth is constant and it's given by the bare coupling J. So then we move the copies closer together. And at some point when the frequency of the modulation equals the bandwidth, so it's roughly on the order of J, you get this resonant coupling between the lowest and first excited band. And this is exactly how you get this gap closing point between Fouquet zones. Or if you want, you just have a resonant mixing between the two bands, the lowest and the first excited band. So you move them closer together, and then the gap closing point can happen at different positions across the dispersion relation or at different quasi-momenta. So if the frequency were chosen to be on this scale, then you would open up an avoided crossing here or induce a gap closing point. And I think I have another example of the spectrum a little bit later. Okay, so what does it mean to measure the topological charge or the sign of the topological charge? Now let's again think about this abstract parameter space Qx, Qy, and lambda. And you can define at the singularity point S how the geometric properties or the Berry curvature in this case vary as a function of these parameters. So I can integrate around a cube if I want in order to determine the flux or singularity at the center. Now, this is something that we cannot do because we cannot really measure these anomalous Hall deflections or do these transport measurements in this abstract parameter space lambda. So the only thing that we can do is extract the value of a Berry curvature by moving a wave packet through a certain region in quasi-momentum space and then measuring the anomalous deflection. But this only works in the Qx, Qy space, not in lambda. Okay, so what we do is you can show analytically that if you take this epsilon now to 0, you can look at how the Berry curvature behaves across the topological phase transition. And I should also say that this axis lambda here goes from just before to just after the phase transition. So it has this epsilon height to epsilon. Okay, so now we look at these two planes and look at how the Berry curvature looks like in Qx, Qy space. Okay, so this we can calculate just by looking at the Fouquet bands as we have done before. And here's an example for a topological phase transition and what happens if you tune across it. But you can show that analytically for this linear gap closing points. So here's the Berry curvature distribution for hexagonal lattice. Here's the K and K prime point. And here it's shown as a diamond, not as a hexagon. So there's two sides of the diamond. These are the reciprocal lattice vectors B1 and B2, which I've shown on one of the first slides when talking about the hexagonal lattice. So here you see there's positive Berry curvature at K and K prime, and there's negative Berry curvature at gamma. So this is at some point after the phase transition. And for this example, the singularity or the gap closing point happens at gamma. And you see that just before the gap closing point, there was actually positive Berry curvature at the gamma point. And what happens is that just before the gap closing, there will be a pi Berry flux developing around the gap closing point, which changes sign across the topological phase transition. And if it turns from red to blue or from blue to red, is governed by the sign of the topological charge, which is either plus or minus 1. So by figuring out what happens with the Berry curvature at the gap closing point allows us to understand how the topology of the band changes. Okay. And in order to extract that, we use the same transport measurements as we had done for the quantum Hall measurement. So again, we look at wave packet dynamics in a semi-classical description. So we start with a BEC or wave packet at the gamma point, which is the lowest energy eigenstate in the system. And then we apply a force in order to move it along a certain trajectory across the dispersion relation. And then, so we can move it, for instance, to just before the gamma point, where we know that the gap closing point happens. And then we look at the displacement of the cloud in C2 after we have moved the cloud across this region of Berry curvature at the gamma point. So we look at the center of mass deflection, which depending on the Berry curvature, there's either no deflection if there's no Berry curvature at all, or it can be either deflected to the left or to the right, depending on if there's positive or negative Berry curvature concentrated around the gamma point. And this allows us, by changing the different parameters of our system, which allow us to tune across the phase transition, to extract this sign change. And this change in sign, which is here in a more complicated notation and what I just said in words. So it's the sign of the deflection just before and the sign of the deflection just after the phase transition point, which happens at QS. From this difference, we can directly extract the sign of the topological charge. Okay, so the way we actually realize this model is a bit similar to the modulation in the bipartite square lattice, but now applied to a hexagonal lattice following this proposal by Kitagawa et al. From 2010. So we use our hexagonal lattice and now periodically change the hopping along the red bonds. So we increase it along the red bonds in this chiral manner. And the realization of the potential, again, works by interfering 3 laser beams. Here, I've denoted again the detuning delta omega just to show that we can also apply forces by accelerating the lattice. But for implementing this modulation, it's actually enough to change the intensity of the laser beam. So if we imbalance these 3 intensities, if they are all the same, we get a symmetric hexagon or hexagonal lattice. If we imbalance the intensity, tunneling along one bond, along one of the 3 bonds will be increased with respect to the other 2. So now we can just periodically modulate these intensities as a function of time, and we do that out of phase. So this is what is shown here for the 3 intensities, I2, I1, I2, I3. And we modulate them in this cosine type manner, shifted by 2 pi over 3 for the 3 beams. And here, these are 3 snapshots during this modulation sequence. Okay, so now in the high frequency limit, it is very similar to the circular shaking of the lattice position, which has been implemented by the photonics people and by Tillmann Esslinger in order to engineer the Haldane model. So if we modulate the tunneling amplitudes in the high frequency limit, we will also get the Haldane model. So this is shown over here. For large modulation frequencies, here on the order of 15 kilohertz. And on the vertical axis is the modulation amplitude, which characterizes the modulation of the strength of the tunnel coupling. Okay, so the Haldane phase is our starting point. High frequency limit, that's what we know very well. So W0, number of edge modes in the middle of the spectrum, is equal to 1, and there's nothing between Fouquet zones. And now you see that something non-trivial is happening when we scan the modulation frequency. So here we tune the modulation frequency to lower and lower values. And the solid blue line determines a phase transition point where a gap in the spectrum closes. Okay, so let me show the spectrum for a finite system. So this is a half semi-infinite strip where we can calculate the spectrum and also see the edge modes appearing. So here they are at 0 energy, and the Churn numbers of the two bands are plus and minus 1, as expected for the Haldane phase. Now, since we are actually working in a Fluke system, there are several copies above, and now we move them closer together in order to create a gap closing point between Fluke zones. So here you see what happens. There has been a gap closing point here, which actually generated now an edge mode in the gap between Fluke zones without doing anything to the edge mode around zero energy. So what we have created is a situation where now we have two edge modes, one around zero energy, one around pi, and the Churn numbers of the bands is equal to 0. And if you decrease the modulation frequency further and further, there's a series of gap closing points, because now you move multiple copies of these Fluke spectra closer and closer into each other. So you mix the bands more and more. And in particular, we studied one more phase where you see a Haldane-like phase again. So there has been another gap closing point now in the middle of the spectrum, which removed this edge mode around zero energy, but kept the one between Fluke zones. And this phase is also characterized by plus and minus 1. But now it has an edge mode between the Fluke zones. So strictly speaking, there's no static representation of that one, because you cannot define the rotating wave approximation limit where you take the frequency to infinity. But there's a simple gauge transformation between this Haldane-like phase and the conventional Haldane phase that we know. Okay, and now you see this abstract parameter space that I've talked about before. So this parameter lambda would be the one that characterizes this white line across the phase diagram. So that's the same parameter space or phase diagram that I've just shown you. But now, instead of having the schematic drawings for the phase transition points, you see the spacing of the two bands. So you see the energy gap between the two bands, evaluated at the gamma point, where the gap closing point happens. So these black lines show where the spectrum or the gap disappears. And then changing the modulation frequency and the modulation amplitude, we can scan across this parameter regime and parameterize this by our lambda parameter. So here you see the energy gap measurements to first pinpoint where the topological phase transition happens. And for this, we use the Stuckelberg oscillations, or this interferometry technique that I've explained before. We use the Stuckelberg interferometry to measure the energy gap at gamma, but we could measure it at any other point. It's just that this one is the most interesting one, because there the gap closing point happens. Okay, so you see that in the high frequency limit, there's a finite gap, which at some point closes for certain parameters of the modulation. So first we scan the modulation frequency, then we scan the modulation amplitude, and then again we scan the modulation frequency. Then we enter the second regime. There the gap increases again, and then there's a second gap closing point happening, which signals a transition to a third topological phase. And this solid line is actually not a fit. It's a band structure calculation where we have the only input parameter that we have used as the calibration of the lattice depth and the modulation amplitude. So these are ab initio calculations with Fluke calculations, which actually match very nicely our experimental prediction. And so we attempted to say that this is the Haldane phase, this is the anomalous phase, but we don't know that yet. So for this, we need the deflection measurements. So the first ingredient we need, as I told you, is to determine which gap closes. Is it the one around zero energy, or is it the one between Fluke zones? And how would that actually even show up in our measurements? So here you see two copies in this extended Fluke zone scheme. And if we use the Stuckelberg interferometry technique, we may either extract the oscillation frequency G0 or the oscillation frequency G pi. But the way we probe it is actually by measuring the system stroboscopically, which actually means that the largest frequency that we can measure is h bar omega half. And so we always measure the smaller one of the two energy gaps. And the sum of the two is, of course, equal to h bar omega. So in the high frequency limit, we are probing G0. And then we can track what happens as a function of the modulation parameters. So now if we change the modulation frequency, these two copies move closer together. And at some point, if we measure the gap here, they will be equal. and that will be exactly equal to h bar omega half. Now, from this point on, if we decrease the modulation frequency further, we move the copies even closer together. But now the smallest frequency is around g pi. So now we actually start to measure the frequency between Floquet zones. So this allows us to determine which one of the energy gaps is actually closing in the experiment. And as you see here, in the high frequency limit, we have a finite value. But then at some point, we reach this cusp, which is exactly at h bar omega half. So here the notion that we are measuring the energy gap around zero energy changes, and we start to measure the energy gap between Floquet zones, which closes as a function of these modulation parameters. So by looking at where these cusps occur, we know which one of the gaps we are probing. So we know that here the gap between Floquet zones is closing, while here, because there was another cusp in between, we know that here the gap around zero energy is closing. Okay, so then the last ingredient that we need is the Berry flux and how it changes as a function of the modulation parameters. Okay, so let's first focus on this little plot up here. That's the Berry curvature distribution of the lowest band in the Haldane phase. So these red points are positive Berry curvature concentrated at the Dirac points at k and k prime. And remember, the gap closing point was identified to happen at the gamma point. So if here you see a measurement of this anomalous Hall deflection when we move the cloud through the gamma point. So since there's basically no Berry curvature, the deflection is essentially zero. The cloud almost does not move transverse to the force that we apply. But now we move closer with our modulation parameters to the topological phase transition. And in this calculated Berry curvature distribution, you see that indeed at this singularity where the gap closing point happens, we find a pi Berry flux that develops at the gamma point, which changes sign across the topologically phase transition. And this you see here as a jump in the anomalous Hall deflection. So first the cloud is deflected towards positive values, and across the phase transition, it changes sign and is deflected to negative values. And from this sign change, we can then extract the value of the topological charge. And then in combination with knowing that the gap between two Floquet zones changes or closes, we know that the winding number in the pi gap has to change by +1. So there is a transition to this anomalous Floquet phase. And now we can do the same thing across the second phase transition, where again, something similar happens. We have this pi Berry flux just before and minus pi just after the phase transition. But now we know that the gap around zero energy closes. So here actually the winding number in the zero gap changes by -1. So using this characterization of the bulk geometric properties of the bands, we actually learn something about the bulk topological properties and how they change across the phase transitions, which would allow us to directly associate the different phases with the anomalous and the Hall phase, or Hall regime, Haldane regime, sorry. And we get the complete set of topological invariants. Now, what would be nice is actually to combine this or these churn number measurements with measurements where you can directly look at the edge states in the system. But for that, we need to modify our experimental setup. So for that, we need to implement a box potential that would allow us to go away from the soft harmonic trap and actually see nice edge modes appearing at the edges of the system. Okay, and that's the last thing I wanted to say for today.
Thank you very much, Monika. Are there now more questions?
Could you comment on what happens as you take this omega to 0? Do you see more phases or what happens?
Yeah, so it becomes more and more complicated because let me go back to this phase diagram here. I mean, if you follow this argument that actually these new phases appear because you shift the Floquet copies more and more into each other, or if you want to have a different picture, you could also think about your original band structure. And if you have a small modulation frequency, you start mixing the bands with each other. So you open small gaps or avoided crossings between states within one band. So this gives you a more complicated band structure. And here the spacing between the different topological phase transitions will become smaller and smaller. So there's a series of phase transition that happens as you move more and more copies into each other.
And at omega equals 0, we should get something trivial, right?
Well, at omega equal to 0, you basically recover the adiabatic limit. So there, I think you would slowly change the tunneling amplitudes along the T1, T2, T3 bonds, and the atoms would follow adiabatically always the lowest band. So in this limit, where you have omega equal to 0, there shouldn't be any mixing anymore, but it's the adiabatic limit where you just deform your band structure slowly, and the atoms have enough time to follow.
So maybe you said this, but the way you measured the Berry's phase in this one, was it the same way that had been done in your example with the hexagonal lattice before, or the honeycomb?
No, in this case, we actually used the transport measurement. So we don't build, and it's actually also something that could have been done, but we just move the cloud through a certain region in quasi-momentum space and look at the anomalous velocity that we find transverse to the force that we apply.
Okay.
And locally, so it works locally because we only populate a small fraction of the quasi-momenta. So in contrast to what we had before, where all quasi-momentum states are populated and you would directly get the Chern number, we just have a small wave packet with a certain width, and we move it through a small region in quasi-momentum space to only probe a fraction of the Berry curvature.
Okay. All right, so for the participants, this is your sort of second to last chance to get to talk to Monika, because we have to wrap up this afternoon. But it is really a great time to ask questions.
I have a question which probably isn't totally well formed, but in Tillman's talk, he also described an experiment that measured, I guess, kind of mapped out this phase diagram of like the delta AB versus the phase, the complex phase, and did this transverse drift measurement to measure the Berry curvature, I guess. So he mentioned that there was a sort of the initial results were kind of like not that great because there was sort of, you would get like a crossing into the upper band, which basically would have you see the opposite Berry curvature, and then and so you kind of got like smeared out, sort of. I'm not describing this totally well, but I guess my question is,
maybe what you mean is that if you have also a fraction in the upper band, since it always has the opposite sign. So in this two-band model, the Berry curvature ideally is just symmetric between the two bands, which is roughly correct in our case. We don't have to worry about the p bands too much, the higher lying bands in the lattice. And if you have a fraction that is also in the higher band, that then this will compensate, or this will reduce the signal that you see in real space, because the fraction that is in the excited band would move in the opposite direction as the ones that you actually want to probe.
Yeah, so I guess my question was, do you have that problem also, or is this a different sort of measurement?
Right, so we did not have this problem. So if I remember correctly, in the first measurements by Tillman, they even did not measure the deflection in real space in the end. But due to a coupling to the harmonic trap, they were able to see the displacement in momentum space again, because it mixes real and momentum space, the harmonic trap. In our case, we had a strong enough signal to actually see the motion directly in real space. So we really took in situ snapshots of the atomic cloud and shows a regime for the force. So we always measure in a regime where there's a gap between the two bands, and we always chose the force such that we remain adiabatically in one of the two bands. So this worked out quite well for us in order to see the deflection in real space. Let me actually see. Yeah, so here you see the order of magnitude of this deflection. So A is the lattice constant, which in our case is something like 300 nanometers. And for these measurements, you get a response which is on the order of 4 lattice constants, which is challenging to resolve. But if you have highly motivated PhD students in the lab, which average many snapshots in order to extract the center of mass very, very precisely, then you are able to resolve that even if you don't have like a quantum gas microscope or something like that. So we averaged like a couple of hundred snapshots in order to reduce the error bar. And then we were actually able to see it directly. But we made sure using these band mapping techniques and measuring the fraction of atoms that is excited to the second band or to the first excited band in order to adapt the value of the force and minimize this fraction.
Yeah, so maybe I can ask a question about, you have mentioned that without using the harmonic drive, you have the opportunity to observe the chiral current, let's say, right? The anomalous 8 states.
Mm-hmm.
So can you say a little bit about that? So it's easy for you to do now, or there are still some issues or some challenge so in that directions?
Yeah, so it's definitely not easy in particular because we don't have in this particular machine, we don't have a quantum gas microscope. So we have a good resolution of around 1 micrometer, which is a few lattice sites. But we have checked numerically when looking at the spectrum that that depending on the sharpness of the hard wall that you project onto your atomic cloud, the group velocity of the edge mode that you're hoping to see quickly decreases. So what happens is actually that in the ideal spectrum, maybe just let me go to this infinite strip spectrum, where you have an edge mode, let's say here in the Haldane phase around 0 energy. The group velocity is essentially given by the slope of this edge mode. But now if you smoothen the hard wall, it starts to get mixed with these bands in a bulk. And so it slows down, which makes it harder to see an experiment, because ideally what we want to do is we want to create this box potential, then create a tiny wave packet in real space with our condensate, move it to the edge, and then see if we can see some chiral propagation. And in theory, like if we do the numerical experiment, this works. But it's very sensitive on the parameters, like it's very sensitive of the sharpness of the wall, but also on the specific position of the wave packet. And this has made it relatively challenging for us to see. We haven't given up yet, but we are going to refine our tools, I think.
Okay, thanks.
All right, so the next session is going to start in 22 minutes. So if there are any closing questions for Monika? All right, so if not, we'll go ahead and close this session. And thank you very much, Monika, for your series of 3 wonderful lectures. And I hope you can make it later on this afternoon, which will be reasonably late in the evening there in Munich for our closing. So thanks very much.
Thanks,
Thank you.
Monika.
Thank you all.
Bye-bye.